Actually, today I will briefly introduce about my project on the bioaccumulation of amyloid fibro and its application. So first of all, why do we have to care about amyloid fibro and what is amyloid fibro? This is an abnormal type of protein that can be found in a series of diseases, include the Alzheimer's disease, Parkinson, Huntington, and type 2 diabetes. There is no doubt that on the cellular scale, these fibers are highly toxic to the human body. However, it has some exciting and extreme property that can be applied in nanotechnology, medical treatment, and even in space exploration. In my project, I study about the method of how to add functional group onto this fiber using the streptavidin and biotin interaction. And I believe that my project will lay a foundation for designing a lot of amyloid fiber that can be applied in nanotechnology to make a nano scaffold that consists of a variety of exciting functionalities. And why do we choose amyloid fiber? In fact, the amyloid fiber only serves this position because it has a lot of unique and extreme property. First of all, this is remarkable stability under various conditions of pH, temperature, and pressure. And it has a highly ordered and very uniform structure that can only be achieved in metals or crystal. And it also has a lot of special reaction sites like the amino group and the hydrophobic aromatic rings. And next, why do I choose the streptavidin and biotin binding system? Their reaction shares some excellent characteristics that make it an excellent bridge system. They have high affinity towards each other, and their interaction has the highest formation constant that ever reported. Moreover, their binding is highly specific, and it can be capable of multiple binding. And the size of biotin is very small, so that it doesn't affect the property of the host molecule. And last but not least, they are all very cheap and commercially available. One of the most obvious applications of the bioaccumulation is that we can use it to characterize and predict the general structure of the insulin amyloid fiber. Recently, a research group in China has managed to synthesize the ultra-thin and super long platinum nanowires using insulin amyloid fiber as a template to add the catalytic platinum on. And these nanowires have very excellent mechanical property that can be applied in nanotechnology. And in my experiment section, I had to bioaccumulate the insulin amyloid fiber using the easy sulfur NHS bioaccumulation kit. And the mechanism is easy to predict. The amino group of the protein will display the sulfur group of the NHS biotin and form a stable amide bond. And then I have to characterize the amount of biotin that attached to the insulin amyloid fiber using the HAMA-amidine assay. And the remaining tasks are to predict the general structure of the insulin amyloid fiber, and then I have to estimate the spacing of the streptavidin on the fiber. As we know, fibers store at different temperature, we have different shape. When stored at room temp, it will have a long and branched shape. However, when stored at lower temperature, it will break apart into smaller fragments that has more exposed surface area and can bind to more high-flammability dye. And this can explain for the difference in the fluorescent intensity when tested under the THT spectroscopy. We can see that the fluorescent intensity of the amyloid fiber stored at negative 20 degrees Celsius is much higher than that stored at room temp. And in the past few weeks, I spent a significant amount of time studying and calculating the dimension of streptavidin, biotin, and insulin fiber. And according to the statistic, the average size of the streptavidin is 4.5 by 4.5 by 5.6 nanometer with a total volume of 113 nanometer cube. And as I mentioned earlier, insulin fiber store at different temperature with general structure of the insulin amyloid fibril is similar to that of the general amyloid fibril. They have extensive layer of beta sheet, and the beta strands are arranged perpendicular to the fibril axis. And when turned into the fibril, the insulin subunit will tend it pre-disulfide bonds. And according to Kurosky, the surface of the insulin amyloid fibril contains 34% of beta sheet and 55% of alpha helix and another system. And there are a variety of important functional groups like the amino, imino, and carboxyl group. Residues like cysteine, tyrosine, histidine, and proline can be found on the surface too. And the presence of proline indicates the existence of loop and stones on the surface of the insulin amyloid fibril. And according to Jake Joy and his co-worker research, the insulin amyloid fibril may obtain either the beta role or beta helix conformation. And the special thing about this conformation is that it allows the exposure of the amino group on the surface of the insulin amyloid fibril, and they will take part in the biotinylation process. The model also allows the flexible C-terminus of the B chain to be exposed on the surface. And from this model, I conclude that one insulin subunit can bind to at most 3 biotin molecules. And into my biotinylation process, first of all, I have to prepare the biotin solution. And I have to add this solution to different types of protein solution and incubate them for 9 hours at room temperature. And we perform time flexibility tests for this fibril before and after biotinylation to assure that the biotinylation doesn't change the property of the amyloid fibril. And the final task to do is to conduct the gamma-amylin assay and to quantify the number of biotin that bind to the fibril. On binding to the streptavidin, biotin will displace the hamidine out of the complex. And this event results in a significant decrease of the absorbance at 500 nanometers. And based on the decrease of decreasing, we can calculate the number of biotin that bind to this fibril. And after doing the biotinylation, my conclusion is that biotin binds to the fibril following this ratio: 2:1 for insulin, 1:3 for fibril stored at room temp, and 1:1 for fibril stored at lower temperature. And I have constructed 3 models to have clarified the spacing of the streptavidin on this fibril. In the first case, at room temperature, 1 streptavidin will bind to 3 insulin subunits, and there is at least 1 biotin every 7 nanometers. And things become more complicated when it comes to fibril stored at lower temperature. The size of the streptavidin is too big to bind on the same side of the fibril. So I have to come up with 2 possibilities to allow the streptavidin to bind on 2 different sides of the fibril. And the first possibility is that insulin will have anti-parallel conformation instead of the normal parallel conformation. And the second possibility is that the insulin amyloid fibril will still retain this parallel conformation. However, to meet the 1:1 binding ratio, the streptavidin will have to bind to the lysine residue on the C terminus of the B chain of the second insulin subunit to maintain the 1:1 binding ratio. And in my final week, I attempt to add the flow 4 cone arrow 565 to the fibril array using the biotinylation process. And we are highly convinced that we are successful in attaching the dye to the fibrils because under the THT fluorescent spectroscopy, we can see the fibril fluoresce at 2 different sets of wavelengths at 482 and chart here, we can see that only the attached amyloid fiber can fluoresce at two different types of wavelength. And under the fluorescent microscopy, we can see that at the very first set of wavelength, 482, the chiroflavin and the amyloid fiber fluoresce with the greenish color. However, with the total different set of wavelength at 592, it fluoresce with the color reddish and shiny red color. And in conclusion, we are successful in introducing the fluorophore anode 565 to the array of fibro. And I strongly convinced that it will create the possibilities for introducing a variety of functionalities onto the fibro and design a nanoscale bioconstruct with more astounding and attractive functionalities. And this is the end of my project. And acknowledgement. I would like to thank Dr. Newson for her advising and very helpful instruction. My lab research group for helping me, and Jean and John, which are student research fund and student faculty research. Any questions?
Questions?
Dr. Newson.
Nice job. And I think you did a good job sort of explaining how you built the architecture and trying to work out where it's binding and how much it's binding. So if you had an unlimited world to work with, what would be the next functional group that you would want to try to attach?
I will try some radioactive particle or magnetic particle because it has a lot of application in real life, and I think can apply it to